this is the strong acid, strong base. Okay, so just to set this up so you understand what's going on. In a volumetric acid-base titration, we're going to use one chemical that we definitely know its concentration to get the other. That's what we're after. We're after, hey, what is the concentration of the unknown? So if you notice, I've got some kind of emptying device. Now the emptying device that we use is called a Buret that we're going to eventually work in lab with, okay? And it comes down to a tip and it's got a valve. Okay, and in that Buret, we normally put the standard solution, okay? You'll hear the word standard. You'll also hear the word, okay, the titrant, because it's important to understand the vocabulary here. All right, in this titration that you played last night, or saw, oh yeah, definitely played last night, and I'll play it again in parts, okay, good times. I had the titrant, or the standardized solution, to be NaOH. Okay, and I knew already that that concentration was 0.12 molar. Okay, and the whole purpose of this, okay, was to find the concentration of my acid. Okay, so I had HCl there. What was that concentration? All right, and so we dropped, and I'll do this a little lower, okay. We had a magnetic stirrer bar on a magnetic stirrer spinning. We also had a pH probe measuring the pH changes per drop or per volume. This is actually measuring milliliters, okay, and I'll talk about that in a second. But we had our base, and I was dropping, okay, drops into an acid solution, which was hydrochloric acid. So we were dropping OH minus into a solution that was already H plus. Okay, and so the whole purpose, okay, of this volumetric titration is to solve the molarity of the unknown. We're going to keep adding this base, and what do we know? We know that the base is going to provide a hydroxide. And let's start, because one of the things you have to do is be able to write a net ion equation here. Okay, so let's go write the net ion equation right on top. Okay, and I'll, in fact, we'll do that to understand what's going on. So try to write it somewhere. It's not on the graph. It's on the graph paper if you have it. And so what did we add? We had a strong acid. That was hydrochloric. I don't know why N got involved, but we had strong acid. So we had hydrochloric acid, who was in the beaker. And by the way, what we call what's in the beaker, we call that the analyte. We're analyzing it. So the analyte is the hydrochloric acid, and the titrant, or the standard solution, is the sodium hydroxide. That's the one we know. Okay, what makes it a titration is we're using a known chemical of a known concentration to figure out the other chemical's concentration through stoichiometry. Okay, so we had hydrochloric acid, and we had a strong base, which was NaOH. Those are the chemicals. All right, well, what do we know? Well, this is a lie. If they're both strong, I would never write this in a net ion equation. I know that HCl completely dissociates. I know that sodium hydroxide is completely soluble. So what's going to be made here, and let me just rewrite this to make this neater, okay, is that I have my HCl and my NaOH. If we were to write that in my net ion reaction and get that wrong, things that are good electrolytes that break apart into free ions. Remember last week, electrolytes, of course, have free ions, are never, ever going to be written together. So these guys dissociate. Now, what do we know about chloride ions? What do we know about sodium ions? They always what? Spectate. They never ionize water. They have no ability to put a proton onto water or yank one. So they're going to spectate, which means on this side, we'll also have sodium plus, okay, and chloride minus. They do nothing. But what we have learned is that water's terrible at breaking apart into its ions, which means it's really good at coming together to make what? Water. So the overall liquid reaction is that H plus a hydroxide makes water. That is your net ion reaction. The net ion equation, so number this 8. Put an 8 in front so I can go find it. Wherever you put it, I'll find it. It's number 8. It's net ion equation. Now, I want to stop and make a point here. Okay, I'm done. But another point I want to make is that this is only going to be your net ion equation if it's strong acid, strong base. You are never going to have this scenario again unless you have strong acid, strong base, and that is very rare. I'm starting with strong acid, strong base, but in chemistry, in analytical chemistry, okay, we're still in using stoichiometry, we almost never have strong acid, strong base again. So don't get in a habit of thinking that there's always the net ion reaction. It's important you understand that, okay? And I'll explain when we get to the other one. All right, so any case, here's a bunch of things that we need. We need the concentration of the acid, the equivalence point, determine the end point of the titration. Okay, we'll put this back up, all right? But I want to get to the things we have to do. So, beautiful titration. Okay, so somewhere, somehow, you got your name up here, okay, write lab 10, and then somewhere, somehow, write your net ion reaction up here, it's number 8. Okay, what you need to do now is you need to identify the equivalence point, okay? Now, to do that, all right, the other day, okay, that the equivalence point in a titration is where all of the protons that were free protons or hydroniums in the beaker have now been matched with the hydroxides that were added. So what you do is you try to find, okay, where this starts to become exponential. Okay, try to find that flat line. And you find this flat line down here, the best that you can. And then try to measure in between. So I'm just going to do this roughly. I'm going to say the flat line is here. So I would take this and draw a line from the most flattest part of my curve. And I would do the same thing here. Draw a line from my most flattest part of the curve. Okay, and then I'm going to take that and I'm going to find a midpoint. For those in geometry, if we had some plots on here, we could definitely do. We could do this a little more accurately with plots on here. So when I do this, I'm looking at 51 centimeters for me. So that's 25.5, right in between those two lines there. And I'm liking that. So there's probably a better way to do it here. So if I insert a line, edit PDF, annotate shapes, and I'll do a line. So I got that, and then do another line. Make another line. Move that up. And then I'm just going to measure. Now, I'm going to use, let's try a measuring tool on this. Probably not. But I'm going to use a ruler. Okay. And for me, when I do it on the iPad, I get 8, so I get 8 centimeters on the iPad. And I can get a 4 about right here. Okay, so for me, there's my dot. Okay, that's my midpoint between those vertical or horizontal, okay, lines there. And I don't need these lines anymore, so I'm gonna get rid of them. I think I can get rid of them. If I can't, I'm just gonna delete them. Okay, so that's my equivalence point. Cool. What is that? Let's write it in. Equivalence. What number is that? I don't know. I'll have to look at that, but it's the equivalence point. Now, what does that equal? That's important. This is where the hydroxides that were what? Added. Remember, we're dropping hydroxides from an emptying device. The Buret is what we're using here. And so we're measuring how much is being dropped. So remember, this y-axis, let's just change it here. This is, let's just put it down here nice and loud. This is what? Volume of OH added. It's always going to be the volume of the titrant added. It's important, okay? So the OH added by the emptying device equals the protons, which we know is synonymous with the H3O+. Okay, and that's something you have to mark up. Okay? Now, something else we should recognize is what the pH is. All right, so I'm going to take my ruler and go across from my equivalence point to find that pH at the equivalence point. That's something else you can graphically do. So I'm going to take another line. For me, I'll take a line, edit the pH, shapes, and I'll just do a line. And then I'll move it. And maybe I'll make it fancy. Oh yes, fancy, pinky up. Nope, I got too fancy. I just want to drag it. I guess I just got to select it. Okay. Now for me, oh, interesting. This is a pH of 6, a pH of 7. All right. Interesting because we have just neutralized what? At that point in the graph, the equivalence point, we have just determined that the pH at the equivalence point, this is pH at the equivalence point, is 7. Makes a lot of sense. All right? Now, of course, the titration kept going. And I want you to understand, we were dropping fluid, okay? And initially that what? The pH wasn't rising much because we had so many more H pluses and hydroxides. The hydroxides weren't making a dent into the H pluses. Every hydroxide that we added hooked up with the H plus to make water. But because there was so many H pluses initially, it wasn't making a fractional dent until we got here. As I said yesterday, if I've got 10, and I'm just making this very simplified, H pluses left, and I drop one hydroxide, that one drop would be 1/10 of a difference, it's of an impact of neutralization. And the next drop would be what? 1/9, 1/8, 1/7, 1/6, 1/5. Hey, one drop could change the pH 20%. 1/4, the next drop would change the pH 25%. 1/3 left. That next drop is 33%. That's why we get this exponential. By the way, this solid line is solid because the actual way that this computer worked is it was measuring the drops. This was the pH at every drop. Why are they stretched out here but so close together here? They're stretched out here because the pH was what happening here? Changing very quickly. And that's why they're stretched out. So this is just showing you the time, how fast it was changing, and then it slowed down again. This is called an asymptote. All right. Now, for us to go after the concentration of the acid, which is, I think, number 1, we need the equivalence point. We just did that. Okay. Now, next step is that we need the equivalence volume. That's what this is about. Exactly how much volume of OH was needed to exactly neutralize all of the H+. Well, I found my point. Now I'm going to make another line down. Okay? So make a line. And I'll make it fancier. and I make a straight line down. Okay, and I'm going to try to read that the best that I can. I don't know if my line is that straight. Okay, but here's what I know. This is 11. No, bad Grodsky. That's 12. This dashes are going every 2, right? Right, because that's 20, so that'd be 12. So this is 12, and this is 14. So you could use a ruler, or we can actually open up LoggerPro, okay, to figure this out. If I was to open up the LoggerPro, and that's why when you're in school you should at some point in time go to self-service and download, you can get this file, and I can drag this right into the LoggerPro file. It'll tell me exactly the milliliter that is. We can just estimate this right now, okay? So for me, okay, if I eyeball it, and you don't have to, you can go into the LoggerPro file, okay? In fact, we could do that right now, okay? Same exact file. Oh, Christmas. Now, I'm going to drag, okay, the cursor right in the middle to find that value. Okay, so I don't know where my cursor is. There you are. So all I'm going to do is drag right there. And you see that, it's hard to see, you can't see it here, but I dragged, and it's actually picking for me the actual data points. So I'm going to scroll up to my heart's content, and it's hard to see where you guys are looking. And I'm going to drag that down. Now if you had this file on your computer, you can do that. So all I did was take my cursor and I dragged it to pick this area, and now I'm going to go find those points, okay? And it looks to me the middle point is 12.65. So 12.65, I think that makes sense. Okay, so based on what, so 12.65, maybe. So I got 12.65 milliliters. Okay, of what? Of base that was added to neutralize. Think of the problems you guys been doing. Hey, what's the molarity of the acid? That it must be if it took 12.65 milliliters of a what? 0.12 molar solution to exactly neutralize 25 milliliters of HCl. Don't forget that this was 25.0 milliliters. You've had these questions. They're actually solved through a lab, okay? So I want you to start thinking about the lab into these questions. So in any case, what do? So I think number one is to solve for the what? The concentration. So I'm going to do that right here. So I'm going to take, and think about this. We've done this before, so this is not new. We know what? Molarity is equal to mole over liter. Okay? So party people, just as a reminder, to get moles, what do? Mole is equal to molarity times liter. Why? Because molarity is mole over liter, right? Mole over liter times liter, you get moles from that. So what we're going to do is, from this 12.65 milliliters, I'm going to convert to liters, right? Because I have to be in liters for this to work. And I get 0.012, was that 6 we said? 0.65. And that's liters. I just converted that milliliters of base. And now I'm going to multiply it by the molarity of the base, which was given to me. I have to know this. It was standardized. It's the titrant. It's 0.12, and that's molar. So molarity times volume is going to give me what? Moles of hydroxide. All right, so I need my liter of calc, because I'm so ready today that I have it ready. Or someone could just multiply that for me. Because I don't know where my calculator is right now. Someone multiply that for me. I think I left my calculator back there.
0.001518.
Okay, my short-term memory is gone at this height, so 0.0.001518. Okay, and what did I just solve for? Moles of hydroxide that were added. We just solved for exactly the moles of hydroxide that were added that do what? that's going to reach equivalence. This is exactly what we do this graph for. But guess what we know at equivalence? Moles of hydroxide added equals the protons. Remember, what we're trying to do here is solve for the concentration, the molarity of the acid. So, party people, I take this, and it's equal to the acid. So 0.001518 moles of H+. That's the cool part. There's your stoich. It's always 1-to-1. But at the equivalence point, we get the equivalence volume, and we converted it. We're able to get the moles of H+. Now, how do we get the molarity of the original solution? That's the purpose. Well, what do I know? Molarity is equal to mole of the H+ over the liter. Well, I told you, party people, we have 25 milliliters in the beaker. So that, of course, is 0.025 liter. And the same moles of hydroxide are the same moles over here. So that's 0.001518. And that, of course, is moles of H+. Put that in your calculator. 0.001518 moles of H+.
Wait, wouldn't the liters be 0.01265?
No, because we have 25 milliliters
okay.
of this analyte. So we found the moles of the hydroxide, which have to equal the moles of the H+. There it is. It's sitting in a solution of 25 milliliters. Take the moles. What do we get with this?
0.06072.
0.06072, and that's the molar concentration of the H+. Hey, HCl is a strong acid, right? So therefore, that must be the concentration also of my acid. HCl's concentration, or molarity, okay, is equal to 0.06072. Probably has too many sig figs here, okay? This has 2 sig figs, and we'll just stay with, let's say we stay with 2, okay? So I probably got to round that to, remember, leading zeros never count, 0.06, okay, 1. And that's our answer, I believe, for number 1. Number 1 is the concentration. I think 2 is the equivalence point. Okay? And that's what we just did there. And yes, I made 0.06. All right? All right, so what else do I have to put up here? Okay, well, let's do the initial pH. Let's verify the initial pH here. What is that number? I'm just going to do an estimate because we're running out of time. I'm going to do an estimate here. So this is 1, this is 2. It looks like the pH here is about 1.6. We can go into the file and just do 1.6. Okay, let's see if I can verify this pH with this concentration. We said the concentration of the acid is 0.061. Concentration of the acid is 0.061. 0.061 of your H+. I can do this. Maybe not. So I got 0.061 is equal to the concentration of my H+, or my HCl. How do I get a pH, guys? If that's the concentration of my H+, or HCl, strong acid, how do I get a pH? What do I do with that? Negative log it, right? What's the negative log of 0.061? Negative log of that number. 1.215, 1.22.
Huh?
It'd just be 1.2.
1.2. Okay, equals your pH. Now what did we just do here? We just showed that if we definitely had 0.016, we should have a pH of 1.2. We got a pH of 1.6. Why is it different? Well, partly due to my pH probes have a tough time at the low ends. Okay, so it's a calibration issue, but it's reflecting. Remember, this is an experiment. Okay, so this is a good verification. Last thing I'm doing here, one of the last things, is let's figure out this last point right here. This is important. I want to verify the final pH. Now, someone said in class yesterday, after the equivalence point, party people, after the equivalence point, the rest, and this is important right here, the rest of this base that's added is excess. This is excess hydroxide added. So the final pH of our titration really is due to extra hydroxides in the total solution. So let's go find, now think about it. Let's go find the total hydroxide. Well, we got 12.65, and we added it to 30. So I'm going to take 30.00 minus 12.65. This is going to tell me exactly the base that was added that was in excess. Okay, what do we get here? 17.35 milliliters of excess what? Hydroxide. Okay, let's go find the moles. We've done this before. Convert this to liters. 0.01735 liters. Times it by the molarity. Hey, that's 0.12. What do we know? Molarity times volume is moles. And we know that's the standard solution. So I'll multiply that together. What do we got for that?
0.002082.
And this is moles of hydroxide. Okay. Now, we need a molarity. We need a concentration of the hydroxide because that'll give me my pOH. So, I'm going to divide this by the volume to get the molarity. Now, this is what's trickier. Pay attention. What volume do I use? I'm not going to use 17.35. Look, the graph. You have to understand. We added 30 milliliters of the base to what? 25 milliliters. So we're going to take 30 plus 25. The total volume is 55 milliliters. So what we're going to do is we're going to divide by 0.055. That gives you the liters. Someone find me that number. 0.002082 divide by 0.055 liters.
0.03785.
3785. And this is equal to the what? Concentration of the hydroxide. I want the pH. So let's go find the pOH. Negative log this. What's the pOH? Negative log of that? Good. Subtract that from 14. Right? Subtract that from 14 and you're going to get your what? Minus 14. Okay, you're going to get your pH. Just pH plus your pOH. So 14 minus 1.42 is 12.58. That is our final pH, 12.58. 12.58. That's what we should get. Now whether our what? Temperature probe show us that. Okay, if I was to look on this, what do I got here? 10, 11, 12, where's that line? Yeah, that's pretty reflective. I think that's definitely very reasonable, 12.58. Okay, we have one little piece left in this. So continuing on, just going over the rubric here, I said determine the concentration of the acid. We're going to label that 1. So where did we do that? That was the work down here. So we found the constant. That's number 1. Okay, determine the equivalence point of the titration. The equivalence point of titration is number 2. determine the end point of the titration. Now, I didn't talk about this in class, but I'm adding to this today right now. So the end point of the titration, okay, would be, if you remember, if we go to table M in your reference table, we know phenolphthalein, which was added to this lab, we know phenolphthalein changed color, probably it seemed like in this area here, but because there's definitely a lag of how fast we can report the pH as it changes, it actually is on up here. So you should know that from a pH of 8 to 9, this is 7, this is 8 to 9, this is the region where phenolphthalein becomes visible permanently. We definitely do see signs in the beaker of it turning that fuchsia color earlier. And when we do a titration with just an indicator, it's important you understand we don't have to use a pH probe to get the equivalence. We can approximate the equivalence, because what does the equivalence point give us? The equivalence point gives us the exact volume that's added. But because titration curves, or because the curve of the titration is asymptotic, almost a straight line near the equivalence point, for reasons we've explained, this line is almost straight up. So if I want to measure the volume added, and that's the key in figuring out what the concentration of my unknown analyte here is, if I use the color change of the phenolphthalein, which will be, okay, in this range here, all right, you can see that up close and personal, how much different is that point from the equivalence point? There is some difference, but there's not going to be a significant difference in the volume. I blew this up, but if you go back to where you were measuring this graphically, okay, the difference of the ruler at the equivalence point to get the volume, and the difference at where we have a color change of a pH isn't significant. You're going to get a very good approximation with an indicator, as long as the color change of the indicator is on the asymptote. And that's key, because they won't always look and have these large asymptotes. We're going to see some titrations, and like the second one you're working on, or will be working on from here, where this this equivalence or this asymptote is going to be shorter. And so you have to pick an indicator that's on this line. And of course, the best way to pick the best indicator is pick one that has a pH color change that's closest to the equivalence point. We're going to learn that its own Ka is that half equivalence point. It's pKa, I should say, is what we do here. So the color change, and I want to talk about the fact that we definitely saw some color changes, and if we didn't do this particular titration with a pH probe, what we would do is we would drop add a drop at a time and see how long the color persists. If you notice, when I added a drop, it was disappearing. Adding another drop, it was disappearing, and then of course it was getting darker and darker. And because we're adding drop on top of a drop, we didn't get a chance for the color change, okay, to disappear. Okay, so the point is, when we do use an indicator, and we will, okay, the color will only persist after 30 seconds in this region. So here, it would have definitely color changed as we added the base. The base is getting close to the H pluses, but as the H pluses neutralize the base, it goes colorless again. So this color has to persist for 30 seconds, and that would happen in this range here. And because that range is still on that straight line, it wouldn't change. So if we stop the titration here, we would still get the same volume, which would lead us to the same concentration of the acid. But it's important you recognize that this area here for phenolphthalein is not the equivalence point. It approximates the equivalence point. So we call this the place where we stop the titration if we use an appropriate indicator where its color change, or pKa, we'll learn about that, is closest to the equivalence point. So we call this the end point. And the end point of the titration is what we would call, hey, we stop the titration if we're just using an indicator. And that would be a very close approximation. I mean, what is the difference between this line and this line? Okay, very, very small when you look at the big picture. So the end point of the titration is where the color change would occur to tell us to stop if we didn't have a pH probe, okay? But what is it? It's just an approximation, and a very good one. It's an approximation of the equivalence point. And if it's an appropriate indicator, meaning it's on this asymptote and close to the equivalence point, it's a very good approximation. And I will say that titrations are very, very accurate, okay, analytical type of procedures. We get right down to exactly what that concentration is. And it doesn't take fancy chemicals to do so. All right, so we've got the endpoint. So we turn to the endpoint, that would be number 3. So this would be number 3 over here. Okay, endpoint, number that please. Number 4, determine the halfway equivalence point. Now, we don't use it for this graph for reasons we'll explain, but the halfway equivalence point would be, well, what would be half the amount of hydroxides you would need to half neutralize? Well, you needed 12.65 milliliters to completely neutralize all of the H+. So the half equivalence point would be half this number, okay? So 6.325 somewhere, and of course we're estimating this, okay? So this is 2, 4, 6, this is 8. So we could probably measure it out. You can also measure it out if I'm using my ruler, okay? Right here is, I could probably do this. Let's use English units. And so I'm getting about 76, so 45.5, and drew that straight down, something like that. 2, 4, 6, 8, yeah. All right, so any case, the halfway equivalence is somewhere right here. And I'm estimating you can actually measure that. And you can measure that what? That volume exactly that it would be, okay? But honestly, you could just take half of that and find that exact value over there. But, so that's half equivalence. And that's gonna be important in our weak acid strong base. Right now, there's a reason why it really doesn't help us here. But what was our number there? So that half equivalence, okay, is number 4. I want you to mark these up with numbers, please. Okay, number 5, confirm the final pH. That's we did over here. That's what this work was here. Okay, and we did all that here. Okay, so that was number 5. All right. And that was the same thing up here as well. I probably should have done the work up here. And then confirm the initial pH. Well, we did that. That's that's gonna be number 6. And that was a little off, okay, but it's okay. On the 4 points of the titration curve, which is the initial, that's the 1, 2, 3, and 4. These are the 4 points, okay? Determine the percentage of acid and base. Okay, well, at point 1, at point 1, we have 100% HA. HA is fancy for an acid. And then we have 0% OH minus. At this point, the half equivalence will have 50%, okay? Now, I really shouldn't write HA because it's not a weak acid, okay? So it's gonna be H+. We have 100% H pluses that we haven't done. And here we have 50% H pluses that we haven't yet, what? Neutralized, but we've neutralized half of them, so half of them remaining, okay? And of course, I can't speak to OH because this is the excess chemical, right? So the OH minus is not present. Any H pluses that I add has been used up to make water, so I can't really speak to that. Now, at this point, we have 0% H pluses that are left in the initial beaker, theoretically, right? Whatever extra H pluses due to the hydrochloric acid dissociating, they're gone, okay? And all of the, what? Hydroxide I used to make that disappear is gone too, because it was what? It was a limiting reagent. We drove this reaction. And again, I can't say enough how this is a driven reaction. Look at this arrow up here. This arrow is showing me that this is a driven reaction. Okay, this is no equilibrium, okay? And of course, we have our pH of 7 at the equivalence point. And then of course, all right, so the last point in terms of percentages, sorry, okay, is here, as we just talked about, this is the excess. This is the excess amount of hydroxides. So party people, we have, at this point here, we have 0%, let's say, H pluses, or we'll just say we have just the excess, I can't really put a number to this, but just excess hydroxides. All right, and that's what we'll talk about. These will make more sense when we get to other titrations, especially the weak acid, strong base that you're going to be doing next. So those are all the points, and that, of course, we had the, oh, I didn't do the net ion reaction, which you should know for strong acid, strong base, as we talked about, okay, is up here, so I'll put this as well. Hey, it's a proton plus a hydroxide, driven reaction, goes to water, and that would be number 8. And there's a reason for that. The chloride ion would what? Spectate, the sodium would spectate. Good stuff. So that's your lab. That's lab 10, okay? And just put lab 10 in your name. And understand the whole point of this lab was, again, what was the concentration of the acid? And we found the concentration of the acid, okay, to be 0.061 molar. Okay, that's the major finding here. All right, so I hope that helps to break lab 10 down in terms of the manipulation of the plot of the pH changes over not time, but volume of the titrant added. Okay, hope that helped.